Hey gang, Math 5500. Starting off where we ended the previous video, we have that our y sub i's are normally distributed with mean beta 0 plus beta 1 x sub I, and of course constant variance. Now we're going to shift to the MLE process. So we're going to have the probability density function, f, so we have our data, given our three parameter values. And of course we know this is 1 over, should have this tattooed to the, to the brain now. Need to write more clearly. Okay, so this is what we know. So the next step is we're going to create the likelihood, create L, as we've referenced it or called it in previous videos. So what I want to do here is again, we just look at the product of the densities and just yeah, don't want to take anything for granted here. So we have 1 sigma 2 pi, square root of 2 pi, e to the minus 1/2. So we have our y1 minus beta 0 plus beta 1 x1. These are not i's. This is actually our first data point. And then we'll go out to our last data point. Okay, so next step, after we get the product of, I'll tell you what, let's pump the brakes a little bit and clean this up just a little bit. So what we have, don't know how I want to do this. Well, the top part, if we think about just this part right here, we can look at the product of the e's minus 1/2 y sub I, and I'm going to distribute the, get rid of the parentheses. And then have this over sigma, let's see. So if we have the product, we're actually going to have n times sigma square root of 2 pi, right? Trying to do this in, no, Douglas. My cat got me distracted, and I'm doing silly things here, which is not cool. So okay, that's, it's basic algebra there, right? So from there, I think we can clean up just a little bit more. So we have the product from I equal 1 to n. I don't know why, but I'm having a hard time focusing on this right now. So we have minus y sub I minus beta 0 minus beta 1 x sub I squared. So we're going to have the we got the negative taken care of. Let's bring the standard deviation out, make it the variance. So 2 divided by 2 times the variance. And then on the bottom, we're going to have so I'll tell you what. Let's rewrite this, and I'll show you what I'm doing. I want to take this to put the square root of 2 pi sigma squared. Of course, this is all to the nth power, and then just put it in exponential form. So we're going to have 2 pi sigma squared to the n over 2. I believe that's right. Yeah, it's not sticking to it. All right. Next thing we want to do is, of course, take the natural log. So we've established L. So next step, let's take the natural log. I promise you I'm going to buy ink. So I don't know if that shows up on your all's end or not. I'm afraid it will, but you know, it is what it is. All right. So where are we? Forgot where we were. Just got a text from my wife. I tell you what, between the cat and the and my wife and all the dinging and stuff. All right. So next step, take the natural log. So what we know from the natural log is, I'll tell you what, I'm going to have to write this over here to keep from going back. So we have the product I equal 1 to n e to the negative y sub I minus beta 0 minus beta 1 x sub I quantity squared over 2 sigma squared all over 2 pi variance n over 2. Okay, now again, this is L, not natural log of L. So transitioning into the natural log of L, we know with the, when we take the natural log of E and take a product, we know it just turns out to be the sum of the exponents. So that's really cool there. So we have minus the sum of our y sub i's over 2 sigma squared. And then we take the natural log of a product. You know, obviously it's we subtract. So if we take the natural log of this, we know that the natural log of something raised to a power is just the power. That's a 2 times the natural log of 2 pi sigma squared. All right, now let's pump the brakes a little bit. Our goal at this stage is to find beta 0, beta 1, sigma squared that maximizes the natural log of L. And these values, of course, are our maximum the MLE, the estimators, and I just refer to those beta 0 hat, beta 1 hat, and sigma squared hat. So if we're following the framework of previous videos and of the MLEs that we've calculated previously, the next step is going to be we're going to take the derivative. But you can actually be kind of clever here and realize that minimizing this part right here is equivalent to maximizing this whole thing. It's kind of a clever trick, I tell you. And the first time I saw this in grad school, and everyone, it's kind of a rite of passage. Everyone in grad school will almost at one time or the other see this approach because it's true. Because ultimately, if you look at this, it should be something similar to you. We actually call this the sum of squares for the residual, which you'll find much more about once we get into ANOVA. But so that again is not like this is not like divided by the sum of squares. But it's kind of cool that minimizing the sum of squares for the residuals, sum of squares for the error, is actually the same thing as maximizing the natural log of L, which is kind of super cool. So again, the MLE and the least squares method that we studied back in lesson 1 in a couple of videos, I believe, give us the same betas. Now, you're probably sitting there thinking, just as I was thinking when I first saw this, seems a little fishy, but it's obvious that minimizing this component right here maximizes the overall value. That's very clear. But it also it seems like cheating, doesn't it? It seems like, we've learned all this process of creating L, taking the natural log, taking the derivative, set it equal to 0, and solving. It seems like cheating. So what I'm going to do in the next video is I'm going to use the more traditional approach to come up with the values for beta hat 0, beta 1 hat, and sigma squared hat. All right, that's all I got. Take care.